Good afternoon. A couple of quick things before we start the lecture today. First thing is your homework is due by 11:59 p.m. tonight. As I've mentioned several times, I don't accept late work, so please make sure you submit it on time. The other thing is to make the lecture a little more seamless. What I'm going to do is the following from now on. I'm going to teach a portion of the lecture, and then I'll see if there are any questions. During that time, I'll try to answer questions as niftily as possible. If I believe that a certain question warrants a longer explanation, or if this is a repetition of what I have just said, maybe we can have that conversation right after class. Okay, and I'll let you know about it as well. All right? This is just so that we make a more streamlined approach towards the material, and I'm more than happy to answer questions, but we will make sure that the content for the day is also conveyed properly and efficiently. All right, okay. Let's begin by talking about mechanical systems. In mechanical systems, we're going to do two things. We're going to look at a physical model, and we're also going to look at the mathematical model of the system. The physical model will be achieved by making use of linear, passive elements. Okay? So this is by the use linear, passive elements, and two words there, linear and passive, begs an explanation, which I'm going to talk about in a minute. The mathematical model will be achieved by applying Newton's laws of mechanics, which you know very well from dynamics. Apply Newton, our good friend. Invariably, the mathematical model is going to end up being a linear ordinary differential equation, or a set of ODEs. So the system model will end up being a linear plural, because we can have systems that have multiple degrees of freedom, and we will end up with multiple equations which are linear, ordinary, and differential. Okay? What is meant by a linear element? This is something that we have looked at the beginning of the semester. A linear element begets a linear relationship between its input and its output. Okay? So there is a linear relationship between and its output. That's an example of a linear element. A passive element is any element that can store energy or dissipate energy but cannot generate energy. Okay? So passive element means that they can store or they can dissipate energy, but cannot generate energy. And the big question is, okay, why are we doing these things? Okay? The reason is as follows. Let's say that I have a mechanical system. Let's say I have the transmission of a car. A transmission is a really complex creature. What's a transmission made of? It's made of even more complicated elements such as gears, such as bearings, such as couplings, such as shafts, nuts, bolts, and so on, right? So if I all of a sudden look at the mathematical model of this really complicated creature, the mathematical model is going to be hugely complicated, something that I will not have the wherewithal to solve and understand at the first basis or at the first level. So what we are doing is we are saying, okay, so be it. This is a complicated thing. I am first going to model this complicated system using these simple, linear, passive elements, which will in turn give me a mathematical model that is reasonably simple for me, which I can then solve and understand the system behavior. But this is the first approximation of that complicated creature. As time proceeds, as our development matures, as our understanding in intellectual prowess enhance over time, we can start adding layers of complexity. We can start saying, okay, this was a simple element, what if I tweak it, and if I make the stiffness of the spring nonlinear and varying with time? How does that change the system behavior? Something of that sort. Okay, you see where I'm going. So, from that point of view, we're going to look at three linear passive elements for mechanical systems, and you've seen these creatures before. They're masses, springs, and dampers, or damping elements. Can everybody see my writing clearly? People in the back. Please let me know, okay? So for today, I'm going to focus on masses and spring elements, predominantly on springs, because masses are fairly trivial, as you will see. Okay, I'm going to push this up. All right. So masses. This is typically used to model the mass of a system. It's as simple as that. Okay, and that can be modeled either as a particle. So if I have a particle, what does that mean? It means that I'm not worried about the geometry of the body. I'm worried only about its mass. So a particle is going to have a weight, mass times acceleration due to gravity. It will not have a geometry. Okay, you know this from dynamics. So this is just going to have a mass m. Typically, I'll just model it as an amorphous blob or maybe a nice rectangular block, but I will not show its dimensions because it's a particle. The Earth is modeled as a particle. If you sit on the sun, you don't want to sit on the sun, but if you do, it's modeled as a particle, right? Because it looks really tiny and it has a certain mass associated with it, right? On the other hand, I want to model human motion. Everybody is a walking pendulum. Everybody is a walking inverted pendulum. We're going to look at that beast in a couple of lectures time. There's nothing simple about the simple pendulum, right? But I would like to model it as a person with an inertia, which means I have a distribution of mass about my center of mass. So I have a certain inertia on top of the mass of the body. That's modeling a rigid body. Right, so this could be some kind of a disk. That disk will have a center of mass. There is a distribution of mass around the center of mass which gives this body its characteristic angular momentum, which you've seen in dynamics, I assume. And we will call that as I suffix g. I will not elaborate on it right now. So Ig is the mass moment of inertia. About center of mass. G. And of course it also has an inherent mass m. So m comma Ig, and sometimes in your book the mass moment of inertia is also characterized by the letter capital J. Okay, so when applicable I'll mention that. This should be fairly straightforward. There should not be any issues understanding this. The next talk about springs. Springs are complicated creatures. They behave in ways that confound us, but we pocket them into a behavior that we understand by saying the following. Any physical body that deforms elastically can be modeled as a spring which stores energy when you load it. Once again, any physical body which deforms elastically, notice the emphasis on the word elastic, which deforms elastically can be modeled as a spring element. Any body that deforms elastically is a spring element. Okay? Spring elements can store energy when you load them. When loaded, when you apply a force on them or when you try to twist them, you apply a torque on them, they store potential energy or what is called as strain energy. Forget the fancy word, just think of it as potential energy. And this energy is recovered when you unload them. They come back to their original shape and size. That's called elastic deformation, which you know from mechanics of materials. Okay, so the energy is recovered. When unloaded. Springs, for us, notice their elastic behavior. Okay, they are not plastically deforming creatures. That's a much more dangerous mode of deformation, which we will not be looking at this semester, probably never. We will model springs using Hooke's law. Okay, so Hooke's law says that the restoring force on a spring, which I'm going to call as F suffix S, and I'll write out the word as well. This is a restoring force on the spring. Is directly proportional to the displacement of the ends of the spring. Is proportional to spring displacement. And you know this. I mean, this is not a new idea by any stretch of imagination. Okay? Depending on whether the spring is used in a translational manner or a torsional manner, this displacement can be a translational displacement of the ends of the spring, or it could be an angular displacement of the ends of the spring. If it's a torsional spring, it's angular. If it is translational, it is a stretch. I will come back to questions. Okay? So what we are going to do next is, I'm going to take a physical system. This is a simple cantilevered beam. And we're going to say, okay, this is too complicated for me, so I'm going to simplify it. How do I simplify it? And then how do I obtain the behavior of the system? Is the question that we're going to answer. And I'm going to do that by means of an example. And hopefully towards the end of class I will have time for one more example. Okay? Now quick question. Yes?
So is it only considered a spring when the energy is fully recovered when it's unloaded?
Absolutely, absolutely. So that is why it means it is deforming elastically. So any body that deforms elastically always comes back to its original size and shape.
So it's a complete elastic.
Completely elastic. That is all. Elastic means completely elastic. There is no other qualification. Elastic or plastic. Okay? All right. So let's take a cantilevered beam, which you have seen in strength of materials. A cantilevered beam is a beam that's fixed at one end and it's free at the other end. Example of a cantilevered beam is a swimming pool springboard. You stand on it, you jump on it, what does the damn thing do? It deflects. What do you do in mechanics of materials? You figure out what the deflection is in a static manner. The force you applied was not a function of time, you see. But now it's a function of time. Okay? So, cantilever. Force applied is a function of time. This is a complicated beast. This is because its behavior or its deflection, right, which is the characteristic behavior of this beam, is spatially distributed. That is, the deflection at the end of the beam is not the same as that at a point in the middle of the beam. So the deflection of the beam is spatially distributed. Not only that, it is also a function of time because the force is a function of time. So what do I see here? I see a system that is dependent on space, that is dependent on time, which means there are multiple independent variables, which means the governing equation that I obtain for this is going to be a partial differential equation. And it's going to be a fourth order PDE. I'm not going to look at it first. I don't like it. I want to simplify it. Right? So here is what we say. It's a spatially distributed response. It is also a function of time. That is, what is a spatially distributed response? The deflection of the beam. And the governing equation that we end up getting, if you apply the principles of mechanics, is a fourth order PDE. Okay, so you end up getting a partial differential equation. So the model is a PDE, which we will not learn techniques on how to solve. Of course, you can solve PDEs, no big deal. But that's not my business here. My business is to take something that is as complicated. It may not look complicated to you, but it is pretty damn complicated. I take something like this and I simplify it using the tools of mechanical systems. Linear passive elements. Here is what we do. Okay? Take the entire beam, lump the mass of that entire beam into a single particle. So that that beam now is going to be drawn in the form of a particle with mass m. This is called as the lump modeling of a spatially distributed system, or a lumped parameter model. Okay? So we are lumping the mass into a particle. Then what we say is, okay, as I apply a force to this cantilevered beam, what does the beam do? The beam undergoes an elastic deformation. This elastic deformation of the beam can be characterized by drawing a spring element, okay? A translational spring in this case. The stiffness of the spring will tell me the nature of the stiffness of the beam itself. Is it a really rigid beam where I have to apply a large force, or is it like a springboard in your swimming pool where the force applied is not really that large and I can see more of a deflection of the beam? Okay, so this is the stiffness of the beam. This is a translational spring. And this models the elastic response of the beam. To some force that is applied to the beam, and I will simplify my life even further by saying, okay, hey, this thing is moving only in the horizontal direction and it's performing one-dimensional motion. Okay, so I will draw some two guides here. and I will say that, okay, this is now the XYZ coordinate system. Hang on a minute. The z-axis coming out of the page. This is now confined to a planar motion, and not only that, there is no motion in the vertical direction, there is motion only in the horizontal direction. This is a simplification of the real system. I am not saying this is how the actual system behaves, but this is an indication of how the actual system might behave. And it's obviously a simpler problem to solve. Okay? So one of you had your hands raised.
So why wouldn't you make it like a radial spring to make it more like similar to the original problem of being deflected like that?
I could just take that system and draw it upside down or vertically. That's fine too. Same thing. It's all the same behavior, right? Or I could do the following. You see, I could say that instead of a force acting on the cantilever, I take the end of the cantilever and twist the heck out of that guy. I can then model this as a torsional spring. Or I could have a combination of both a torsional spring and a translational spring. Okay? One last question. You had a question.
Yeah, I was just wondering, just clarification really quickly, when you said model of PDE, what does that mean?
A partial differential equation, because what will end up is that the mathematical model will not only be a function of time, it will be a function of space as well. So it will have multiple independent variables. Okay? So this system model will end up being an ODE. And mind you, I have made some simplifications which I haven't explained clearly by saying I am ignoring all sources of friction here. That's a huge if. Right? But then what I'm going to do on Wednesday is I'm going to say, okay, let's model friction in this body, which means that the materials within the beam, they are sliding relative to each other as I deflect the beam, which means there is some rubbing going on, which means there is dissipation of energy in the form of heat. This dissipation can be modeled by means of a damping element or a damper, which I will add right below the spring. But that's a complication I'm going to do on Wednesday. For today, this is all we're going to look at. And what I'm going to do is obtain the equation of motion of this simple little system that I'm pretty sure you've seen in dynamics. But forget everything you learned in dynamics. Okay? We're going to do it in a different way. Alright, so first things first. I'm going to take that spring mass system. My aim is to obtain the system response to the force. Here is my system. This term K is called the stiffness of the spring, which you have come across in the past, and I'm going to use that very soon. Okay, so K is the stiffness of the spring. Before we solve anything, we always set up a coordinate system. Okay, this is a must. So I set up a coordinate system: x-axis, y-axis, z-axis. Then I list the assumptions that are involved in the problem. This is a simple model of that cantilevered beam. I want to obtain the system response. What are my assumptions? I am ignoring friction. We will include friction later. Okay, please don't worry about it. It's going to be an integral part of your life and a pretty confusing part of your life. We will also assume that the motion of this body, this cantilevered beam, is one-dimensional. Okay, it is restricted to the horizontal plane. So one-dimensional motion. Right. So what is our aim? Obtain the system response, which means obtain the mathematical model of the system to the force that is applied. And later on, once we start learning Laplace transforms and so on, we will solve the ordinary differential equation and actually obtain a system response by plotting it as a function of time. Okay? First things first. Whenever you look at a mechanical system, you have to define what is the number of degrees of freedom of that system. You must have heard this term in dynamics. We're going to give it a slightly different spin so that we can use it very easily. Okay? So degree of freedom. My shorthand notation is DOF. Look at the definition. This is the only time I'm going to go over it. It is the minimum number of independent variables that describe the position of the mass at any point in time. Okay? So the minimum number of independent variables that specify the position of the system at any time. Two words: minimum, independent, and in the presence of constraints. Presence of all constraints. The third word is constraint, or constraints. Constraint, as you know and as you have faced in your own life, is lack of freedom. So many systems are constrained to behave in certain ways. What's a constraint for our mass here? Our mass is constrained to move only in the horizontal direction, which means that there is no motion in the z direction, there is no motion in the y direction. So how many constraints are imposed upon this mass? Two constraints. How many constraints are imposed upon this mass? Two constraints. It cannot move vertically. It cannot move out of the page. It can move only in one direction. Okay? So typically constraints will be called by the letter C, capital C. Okay? So when I say C, it implies the number of constraints. Then I'm going to slide this up and write a quick formula. Here is the formula. Number of degrees of freedom, DOF, D with an S on the top, the subscript means degrees of freedom. Okay? The number of degrees of freedom is 6R plus 3P minus C. It's a strange looking thing. What's R, what's P, and what's C? C, you know, the number of constraints. Okay? So C is the total number of constraints. What's R? The total number of rigid bodies in the system. total number of rigid bodies in the system. Can you tell me what's little b? Yes? Planes? Yes? Particles. If I've taken care of rigid bodies, why leave the poor particles alone? Right? So P represents the number of particles. Total number of particles in the system. What does the 6 and the 3 represent? Can somebody tell me? Yes, yes.
Rigid bodies have translational motion in X, Y, and Z and rotational motion in X, Y, and Z.
Beautiful, 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 fantastic. And somebody else had their hand raised too? Was it the same answer?
You basically, for the particles, it's just a translation.
For the particle, just a translation. Fantastic. So what we are both alluding to is the total number of motions possible by an unconstrained rigid body and an unconstrained particle. If I have an unconstrained particle, I just take a marble and leave it in space. How many variables do I need to know to locate its position in time? I need 3. Position in X, position in Y, position in Z. If I have a rigid body, unconstrained, untethered to mortal attachment, how many variables do I know? I need to know the location of the center of mass of the rigid body. That's 3 coordinates. And I need to know 3 rotations as well. So that's a total of 6 variables. Okay, excellent. So the 3 and the 6, I'm going to write it down. The 6 are, I'm sorry. And the 3 P, the total number of variables to describe location in space for any time in the absence of constraints. Dynamics is difficult. There is no shortcut, there is no 2 ways about it. Okay? The only saving grace is if you are methodical. Set up the coordinate system first. Figure out the number of degrees of freedom by figuring out how many particles are there, how many rigid bodies are there, and how many constraints are there in the system. Then we find out, okay, this is the number of degrees of freedom. So for our system, how many rigid bodies are there? If I consider the spring and the mass, there are no rigid bodies. This is just a particle. So for us, R is equal to 0. Number of particles is 1. Number of constraints is 2. Which means that the number of degrees of freedom is 6 times 0, 3 times 1, minus 2. Which means that I have only 1 degree of freedom. Okay, so this is for our system, okay, which is that spring mass system that I just drew, okay, which is right there. And I'm going to pull that panel down, and then I'm going to start labeling the degree of freedom. Number of degrees of freedom is 1. And now comes the very, very difficult art in dynamics. What variable should you choose as the degree of freedom? And there are no shortcuts for this either. It has to come from practice. It has to come from solving several different types of problems and some common sense. Okay, common sense tells me that, okay, what could be the variable that defines where the mass is at any point in time? It could be the horizontal position of the mass. And I can call that variable as x of t, x being a function of time. Okay, so for me, for this particular system, the degree of freedom is x of t. Okay, so for us, x of t is the degree of freedom, and if x of t is the degree of freedom, the expectation is that we will end up with an ordinary differential equation with x of t as the dependent variable. Okay, so x of t, so we will end up with an ODE with x of t as the dependent variable. And we are going to see how that's going to come about, okay, which you have seen in dynamics, so this is in some sense a recap, but maybe this is more methodical than what you've seen in the past. Before we do that, okay, we're going to do something that is really, really important to me. This is, if I do not see this happening in your work, it is sacrilege. Such papers are anathema to me, to my existence, and I will take it out of you. Okay? And what I mean by that is, I mean a coordinate system with a sign convention. That is, I have figured out that x of t is the variable that defines the degree of freedom, but when is x of t positive? Is it when the spring is moving to the right or is it to the left? I need to know that. If I do not know that, then the problem makes no sense to me. The solution makes no sense to me. You're saying the spring is 5 meters from some position. Okay, is it 5 meters to the left or to the right of the damn thing? Otherwise it makes no sense, you see. So we are giving it a physical grounding. Okay, so sign convention. I'm going to use this figure as a template for the sign convention. First things first, I'm going to mark the static equilibrium position of the system. Okay? It is called the SEP. So static equilibrium position. This is the position of the system when the spring is unstretched. This is the system position. That means there are no external forces acting on the spring. Okay? That is SEP. For every mechanical system, we will figure out what is the SEP. Okay? In this system, it's quite obvious when there are no forces acting on the mass, the spring is at its unstretched or its original length. And the position of the mass at that location is called SEP. This is how I typically mark it. With a hatched line which says this is the beginning of all things. This is the mother of all things. Okay? Then we say, okay, this is my choice, as it is your choice. I am going to say that all displacements that are to the right of the SEP are considered to be positive. So I'm going to mark that by saying, okay, this is an arrow, and this indicates the positive direction of the displacement. What does this mean? It does not mean that the mass is traveling in that direction. No. All it means is if the mass is traveling in that direction, its displacement is taken to be positive. If the mass were traveling in the opposite direction, its displacement would be negative. That's all it means. It does not tell you that the mass is traveling this way. Okay, please keep that in mind. Alright? Once I do that, then by basic physics, the direction of the positive velocity has to be the same as the direction of the positive displacement, because velocity is displacement divided by time. We always move forward in time in system dynamics. We don't go back in time. So time is always positive for us. Which means if I choose the direction of the displacement to be positive to the right of the SEP, the direction of the velocity also has to be positive to the right of the SEP. And so I'm going to mark this by saying this is plus x dot direction as well. Does this make sense to everybody? One more time. By basic physics, velocity is displacement by time. Time is always positive for us. So the positive direction of velocity is the same as the positive direction of displacement, and by the same argument, the positive direction of acceleration has to be the same as the positive direction of the velocity, which is the same as the positive direction of the displacement. So moral of the story, all you have to do, figure out the SEP, mark the direction of the positive displacement. This will automatically ensure the direction of positive velocity and acceleration are in the same direction as that of the displacement. Okay? Acceleration is velocity by time. Time is positive, so acceleration is positive if velocity is positive. Velocity is positive if displacement is positive. When is displacement positive? When the mass is traveling to the right of the SEP. Once we are done with all this, whatever force acts on this mass will be taken to be positive if it is along the positive displacement direction. If it is pointing opposite to it, it will be taken negative. And tomorrow I can come and tell you that all of this is wrong. I am going to choose the direction pointing to the left as the positive displacement, and my answer should not change. The physics of the problem cannot change based on where you get up in your home. This is just a Sine convention. It's a road map. It does not change where you end up. Okay? I want to be very, very clear about it. This is what I follow. I expect you to follow this as well. And this is the only way to solve this problem. Okay? So with that said, and with your permission, I'm going to erase this panel of the book. And all of these will be posted in my notes as well. And now we are going to solve the problem. I'm going to say, okay, apply a force on the mass. Okay? And I'm going to draw two things. I'm going to draw the unstretched position of the mass with the spring. This is the coordinate system, okay? Then I apply a force on this mass, and if my displacement is positive, hang on, I'll just complete this thought and then I'll come back to you, okay? If the displacement is positive, F of t is the force acting on the mass. The spring has been displaced by an amount x of t. From its equilibrium position, This is the displacement of the spring. And so, the unstretched length of the spring was L naught, let's say. The stretched length of the spring is L naught plus, if I assume the mass to be traveling to the right, it's plus x of t. And so the spring displacement is the stretched minus the unstretched length of the spring. Displacement of the spring is L naught plus x minus L naught. Notice this, it is the stretched length minus the unstretched length. And so this is x of t. And what this says is the following. If x of t is positive, the spring is in tension. If x of t is negative, the spring is in compression. And I'm going to assume that x of t is positive. For x of t greater than 0, the spring is in tension. I'm going to draw the free body diagram of the spring, the free body diagram of the mass, and the kinetic diagram of the mass. Some of you may know it, some of you may not know it. I'm going to explain that. Okay? I'll answer your questions towards the end. Pardon me. I want to complete this thought process. So if x of t greater than 0, the spring is in tension.